Good afternoon, everyone, and welcome to the EOL seminar series. Our speaker today is EOL's very own Dr. Junkyung Kay. Dr. Kay received his education at Yonsei University in South Korea in the Department of Atmospheric Sciences. His dissertation on evaluating ensemble predictions using data assimilation systems won him the Best PhD Thesis Award at the Korean Meteorological Society. With such an accolade under his belt, as well as a service recognition award from the same society, Dr. Kay crossed the Pacific Ocean to continue his modeling career as a postdoc, first at the University of Oklahoma, and then here at EOL with Dr. Win-Chao Lee. Currently, Dr. Kay is a project scientist at EOL's remote sensing facility, where he works closely with Dr. Tammy Weckworth and the MicroPulse Dial group, assimilating their measurements of water vapor profiles. Junkyung's expertise in data assimilation of lower tropospheric water vapor observations is an advantageous partnership with the MPD group and happens to be the topic of his seminar today, which is on the role of MPD water vapor profiles in improving convective-scale weather predictions. We are using Slido to pose questions, which you can ask at any time during the seminar. The Slido window is located below this presentation screen. Don't panic if you do not see your question pop up immediately. We archive all questions until the end of the speaker's presentation, where they will be revealed during the Q&A portion of the talk. Dr. Junkyung Kay, we welcome you, and the virtual stage is now yours.
Thank you, Jackie, for kind introduction. I'm Junkyung Kay of EOL, and today's title is the role of MPD water vapor profiles in improving convective-scale weather prediction. So before I start, I would like to acknowledge my collaborators, Tammy Weckworth, Win-Chao Lee, Jenny Sun, Glenn Lomine, and Matt Heyman from NCAR, and Dave Turner from NOAA, and Michael Ng, who was a former AHP postdoc, and he's working now as in the NERSC. Okay, the atmospheric boundary layer impact our society in the form of daily weather and air quality. So the accuracy of a modeled atmospheric boundary layer structure critically depend on the initial conditions and the specific surface parameters and the kind of formulation to represent surface and turbulent processes, and the effective simulation of major scale and large scale dynamics. So to get accurate initial condition, so dynamic and thermodynamic profiles having a very high temporal and vertical resolution are required. The existing current vertical profile in the ABL is the zone and aircraft data, and they are too raw to resolve these micro and major scale features. So these days, the ground-based remote sensors are developed, and the left figure shows the example of these ABL profiles, the ARRI and the flow wind lidar and MPD. And they measure the different types of variable and have a very different vertical range. And the water vapor in the lower atmosphere plays a critical role for the development of cloud and deep convection. So the cloud and convection are highly sensitive to the small change of water vapor in numerical simulation. So the NCAR and Montana State University jointly developed water vapor MicroPulse Differential absorption lidar, MPD. And MPD is very advanced, eye-safe, autonomous, lidar-based active remote sensing, and it measures the absolute humidity and temperature with a very high temporal and vertical resolution. So the key question in this talk is what is the role of MPD water vapor profile in improving numerical weather prediction? So along these questions, I have several scientific objectives to answer here. The first, I would like to evaluate the improvement of the high impact weather analysis and forecasting skill by assimilating the MPD water vapor profile observation. And then we would like to understand the impact of MPD water vapor profile from dynamic and thermodynamic point of view. And then we try to assess the combined and individual impact of MPD and other ABL observations, such as the flow in the lidar array. And lastly, we would like to determine the optimal density and spacing of MPD site to support a nationwide network of MPD sensors to improve the forecasting skill. So this is the outline of my talk. It is consists of 3 parts. I will show the data assimilation result using the OSSE and OSE here. To help you understand better, I will briefly explain what is the OC and OSE here, and what is the difference between them. Before we build the observation network, we would like to evaluate the potential impact of this observation in advance. So we generate a simulated true state, which is very realistic and accurate atmosphere. So from this simulated true state, we can make an observation data set and assimilate them to know their impact. On the other hand, if we have a real data observation set, then we can directly assimilate them and evaluate the observation impact. So we call this experiment as the OSE, and the main difference between the OC and the OSE is that we can assimilate the simulated observation or the real observation. And lastly, I will introduce some data assimilation challenges for our MPD water vapor moisture observation. Okay, I will show the result of OC experiment. The title is the study of the impact of MPD water vapor profiles on convective weather forecasting using observing system simulation experiment, OC. This study examined a large long-lived MCS in western Kansas during the night of 14 to 15 July and observed during the pecan field campaign. At 02 UTC, widespread convection merged, and the MCS originated in the western Kansas, eastern Colorado here. And the 3 UTC, we can find the multiple outflow here, and 4 UTC, the MCS formed and covered all of western Kansas. Okay, as I explained before, the OC need the naturon that is assumed to be the true state of the atmosphere, and it should be very realistic and accurate state. To generate, and also we need the control run that is kind of a reference state we would like to improve by data assimilation. So I have make a faulty ensemble simulation and choose the best performing member as the nature run and choose the worst performing member as the control run here. And this is the real radar observation, and this is the selected nature run and the selected control run here. For this selecting procedure, I applied the objective analysis called mode analysis. They evaluate the performance of this member in terms of intensity, shape, location, and the evolution of the convection. So this is the evolution of convection from the nature run and the control run. The first row shows the observation or the radar, and this simulation, the nature run just simulate consistent convection initiation and its evolution with the real rate observation. And in other hand, control run, it simulate no convective system here. Okay, this is the experimental design. I used the WAF model with a 15 and 3 kilometer resolution. And I used the DART ensemble data assimilation system using the 50 ensemble member. As I explained before, I made a nature run and I make a simulated observation from this nature run. And this table describes some model configuration used for the nature run and control run and the data assimilation experiment. Okay, because the SOND is some representative profiling instrument that are routinely assimilated in the operational center. So we will evaluate the impact of MPD being deployed at the current SOND site and verify that MPD can complement the existing water vapor profile from the observation of this SOND site. So MPD are co-located at the SOND site, shown this left figure. There are 45 SOND sites over the corners, and there are 15 SOND sites in our inner domain. And this shows the location of our MPD and SOND site. Okay, the control run is the reference state without any data assimilation. So we want to assimilate this observation into this control run and improve this simulation. So we have conducted 4 different data assimilation experiments. First, we just assimilate the surface observation, and we call it as a experimental surface. And also we assimilate the wind, temperature, and pressure profile from the SOND data. So we call it this experiment as the surface plus SUTP. The S means the SOND data here. And also we assimilate additional Q profile from SOND data. So we call this experiment as the surface plus SUTP plus SQ. And instead of the SOND Q observation, we assimilated the MPD observation. And so we call this experiment as the surface plus SUTP plus MQ here. Okay, this is the result. The reflectivity forecast, the first 2 rows shows the nature run and the control run here. And this nature run is overrated as the red solid line in the other experiment. So when we just verify the convention observation impact, these 3 experiments, they fail to assimilate the southern part of the convective system here, like this. And when we assimilated the SOND data, it has very little impact on this prediction. So they shows very little differences between this experiment. And when assimilating the MPD data, it improved the simulation, especially at the southern part of the convective system, and also it increased the intensity of the convection and the structure well. And this is the fractional skill score for 1 hour accumulated precipitation forecast. The equation of this fractional skill score is shown in the left. And the higher the better. So the magenta line, it shows the result of assimilating the MPD observation. So the MPD shows the highest skill score, and followed by this green line and the blue line, the result of assimilating the surface and the SOND data. This result is valid for almost all threshold and radius of influence for almost all forecast lead time. So the previous 2 slides, I have shown that the MPD has very good positive impact in terms of the qualitative and quantitative verification. So I'd like to investigate why the MPD has the positive impact for the forecast. So this is the analysis field that used for the initialization of the forecast. So the wind field and the surface wind field and the precipitable water here. And when we assimilate the surface observation, it improved the surface wind field like this, and the wind field of history compared to the control run. And SOND data cannot change the water vapor field in the analysis field. And when we assimilate the MPD, that increased the water vapor amount, especially over the Oklahoma and the Kansas compared to the other DA experiment. The right figure shows the time series of precipitable water averaged over the inner domain. The x-axis shows the data assimilation cycle or time, and y-axis shows the area averaged water vapor, precipitable water. So it shows that the assimilation of MPD with a multiple DA cycle, the magenta line, it continuously improves the water vapor amount in this domain. And this is the height longitude cross section for water vapor mixing ratio. The first figure shows the full field of nature run, and this cross section along line A and B here. This water vapor mixing ratio from nature run shows that there is an elevated moist air ahead of this MCS. This solid and dotted line shows the vertical velocity. So we can find the very elevated moist air ahead of this MCS. And the other figure shows the difference field between the DA experiment and the nature run. So this blue color means that this simulation has the dry bias. So when you see the control run here, we can see the prominent dry biases here, and assimilating this conventional observation reduce this dry bias below 2 kilometer height in these 3 experiments. And also in particular, assimilating this MPD improved the dry bias through a deep layer more than the conventional observation. Okay, in the previous section, we have co-located the MPD instrument with the operational on the site and have verified the positive MPD impact. In this section, to further investigate the observational capability of a nationwide network of MPD instrument, we explore other potential configuration of MPD network. So in this figure, the simulated MPDs are deployed at random location, giving a range of distance from the 70 kilometer spacing to 380 kilometer spacing. So the total number of MPD site is about 600 for this 70 kilometer spacing, and about 30 MPD site for this 380 kilometer spacing. Okay, this is the fractional ski score for the different configuration of MPD site. And the left figure shows the fractional ski score for light precipitation, and the right figure shows the fractional ski score for intense convective precipitation. The result shows that as the MPD spacing increase from 7 kilometer to 380 kilometer, the experiment predict light precipitation better. So this blue line has the highest ski score than this black line, the 70 kilometer spacing. And as on the other hand, for this intense precipitation, as the MPD spacing decrease from 380 kilometer to 130 kilometer, the MPD has more impact on intense precipitation. So this contradictory result implies that the optimal spacing of MPD is very dependent to the intensity of a precipitation event. This is maybe because the intense convective precipitation results from the complex multi-scale interaction between the ambient flow and the convection. So the dense network of the MPD can resolve the fine scale of variability of this system. On the other hand, for this light precipitation, that is usually the accuracy of this light precipitation is affected by the more large scale environment. So the figure C shows the surface pressure tendency, and it's a measure of dynamic imbalance at a synoptic large scale. And it shows that the very dense spacing of the network, for example, the 70 kilometer spacing has the highest score of pressure tendency, it indicating that the dense MPD network can cause some imbalance in the in the analysis field. So this imbalance caused this lowest skill score of 70 kilometer spacing. So the sparse MPD network with a greater than 200 kilometer spacing had a significant impact on the light precipitation prediction due to more balanced initial condition. So this is summary of our OSSE study. The short-term forecast of convection initiation, the evolution, and the precipitation of the MCS are improved by assimilating the MPD profile data in comparison to assimilating the conventional observation. And the conventional surface observation correct the surface warm front structure and the location, and the MPD improved the low to middle level moisture field within the warm sector of the front. And the improvement of convective intensity and the evolution is attributed to the correction of elevated moist air ahead of this MCS, which benefit from the frequent and continuous update of the MPD oral vapor profile data. And more dense MPD network result in better performance for convective intense precipitation, while degrading light precipitation performance due to the imbalance of analysis field at large scale. Okay, in this part, I will introduce the result of OSE, and the title is the impact of assimilating low atmospheric wind and thermodynamic profiles on convective weather forecast over the corners using the OSE. The first field campaign of a network of 5 MPD called the MPD Network Demonstration Project combined the observational capability of the MPD area and the Doppler wind lidar at 5 DOE SGP field site from 22 April to 19 July 2019. And during this field campaign, the temperature and the water vapor profile from area and the water vapor profile from the MPD and the wind profile from the Doppler wind lidar were collected to supplement the existing weather radar wind profile and the surface station data. And this table summarized the detail about these 3 ABL profiles. And the left figure shows the location of the deployment site near Lemont, Oklahoma. So we utilized data from this 3 months field campaign for our OSSE study. And this is the left figure shows the map of our 5 SGP site. And we shows the example of time height cross section of MPD area and the lidar observation. So we examine one precipitation case on 14 June 2019. And the real observation, radar observation shows the convective system, and this black box shows our targeted area. And this weather chart shows that there was a balcony instability and the thermal advection and the low level jet transport the moisture into our targeted area. So the left figure shows the observation site distribution. So we assimilated the conventional observation and the ABL profile observation. So the table summarized our DA experiment. So first, we just assimilate the conventional observation, including the surface station data, zone and satellite wind, and other marine observation. So we call this experiment as the experiment conventional observation experiment. And we assimilated all conventional observation and the Doppler wind lidar, MPD, and area data. So we call this experiment as the all experiment. And the experiment area, we assimilate the conventional observation and Doppler lidar and area data. And MPD experiment means that we assimilate the conventional observation and Doppler lidar and MPD. And we use the same model and data assimilation system as our previous OSSE experiment. But I increased the ensemble size from 50 to 60 member. And this is the time schematic flow of our experiment. And I assimilate the conventional observation at every 3-hour interval from the 0 UTC 13 June to 03 UTC 14 June here. And I start to simulate the conventional observation and the ABL profiles at every 15 minutes for 3 hours. Okay, this is the result. The first row shows the radar observation, and when the reflectivity forecast shows that when we assimilate the all observation here, the all experiment, the simulation predict more organized and strong convection, which is more consistent with the observation compared to the conventional observation experiment. And when we compare this ARI and MPD experiment, the assimilating the MPD mostly attribute this improvement of this old experiment is mainly attributed by the MPD data than ARI data. And the right figure shows the fractional skill score for 1 hour accumulated precipitation. And this result is very consistent with the reflectivity forecast. So the all experiment, the green line shows the highest skill score and followed by the MPD and ARI experiment. Especially at the early forecast lead time, the blue color, the MPD shows very similar skill score with the all experiment. And the ARI data improved the forecast compared to the conventional observation. However, the impact is very limited compared to the MPD data. In the previous slide, I verified all forecast from the deterministic forecast. However, one advantage of ensemble data simulation is that we can conduct the ensemble forecast. So we have a calculate the forecast probability from ensemble forecast, and this NEP, the neighborhood ensemble probability, this NEP measure the probability of this event induced using the ensemble member. So the first figure shows the observation of precipitation, and the experiment all shows the best ensemble forecast in terms of this NEP. And when we assimilate the conventional observation, then the ensemble member predict the wrong horizontal distribution with a different orientation, like this, compared to the real observation. And assimilating the MPD correct this horizontal distribution error and also improve the forecast in the northern part of the system. But assimilating the ARI shows very little impact on this ensemble probability forecasting. So from this previous result, we have verified that the positive impact on the ensemble forecast and also deterministic forecast. So this is the I would like to investigate the impact of MPD on the initial condition and all analysis field. So this is the vertical structure of thermodynamic analysis at this observing site. So this solid line is the analysis or initial condition, and this dotted line is the observation from zone. Okay, this when we just assimilate the conventional observation, we can find the wet bias in this area, this level, and also find the warm bias here. And assimilating the ARI data correct this warm bias. But however, there are still this wet bias are remained here. And also when we assimilate the MPD data, this MPD correct this low level wet bias. So when we assimilate the all observation, including the MPD and ARI data, this analysis shows much consistent structure of temperature and water vapor field in particular structure, consistent with observation. Okay, this is the height, longitude cross section along the line A and B. Okay, the first figure shows the full field from all experiment, and other figure shows the difference field between the other DA experiment and the all experiment. So the first, when we see this water vapor mixing ratio analysis field, we can find a very elevated moist layer the west of the observing site. This triangle shows the location of our observing site. So there are elevated moist air layer and much drier layer here. And when you assimilate the conventional observation, these simulations have a very wet biases compared to the old experiment, and much dry biases here. And this MPD contribute to lowering this water vapor mixing ratio east of the site, and also increase this water vapor mixing ratio west of the site. And also area contribute to lowering this water vapor mixing ratio, but this impact is very constrained to the near surface here. And however, on the other hand, the area contribute to lowering the temperature below 2.5 kilometer height. And so this combined MPD and area data make the air drier east of the site and cooler at the low level. So this combined the evaporating impact correct the horizontal distribution of precipitation. So this is summary of our OSE study. The short-term forecast of precipitation of the MCS are improved by the simulating all MPD area and Doppler lidar profiling data compared to the conventional observation. And this assimilating MPD water vapor profile contribute the most to improving precipitation forecasting skill. And the area improved the temperature profile below the 700 hectopascal. And this improvement of precipitation forecast is attributed to the correction of moist air east of the precipitation system, which improved the horizontal distribution of the precipitation forecast around this site. Okay, in the previous OSE and OSE study, we have investigated the MPD impact on convective precipitation forecast event. And we are also interested in the MPD impact on non-precipitation event, focusing on the prediction of the ABL structure and its evolution. So the motivation is like this. The transition from the convective boundary layer during the daytime to the stable boundary layer during nighttime after sunset play an important role in the change of structure of turbulence. But our knowledge regarding this transition and its feedback on the structure of the nocturnal boundary layer is limited from both modeling and observation perspective. The lack of knowledge of this transition prevent accurate prediction of the onset and development of the nighttime boundary layer. So we would like to evaluate the observation impact from assimilation of the MPD area and the lidar profile to improve this prediction of the ABL transition. So we assimilated our ABL profile using the modern system that has very similar configuration with the operational Haar model for non-precipitation event during the MPD demonstration project. And this is the experimental design. We have conducted very simple 3 different data assimilation experiment. The experiment means that we assimilate just conventional observation, and experimental MPD means that we assimilate the conventional observation and the MPD data. And the experimental MPD plus Doppler lidar means that we assimilate the conventional observation and MPD and Doppler wind profile data together. We use the same domain as our previous OSSE and OSE. However, we use the different physical parameterization set, which is much similar with the operational Hull model. And we use the same DART ensemble data assimilation system using the 60 ensemble member. And this is the very preliminary result. So the left figure shows the time series of water vapor mixing ratio observation from Raman lidar and height time cross section. And this middle panel shows the forecast from the 3 different experiment, and simulating this different set of conventional and the ABL profiles should result in a very different initial condition and different features of the PBL structure with time, especially during this transition period. So interesting result is that the right panel shows the time series of PBL height and surface pressure, surface temperature, and the humidity. So the PBL height time series shows that assimilating the MPD and Doppler lidar intensify the turbulence and increase the PBL height compared to the simulating the conventional observation, and leading to more active mixing process. So the surface specific humidity field has been decreased compared to the simulating just conventional observation. So this preliminary result shows that the PBL structure of the evening transition is very sensitive to the ABL observation, and the effect of our ABL profile DA lasted about 6 hours. So by further analyzing this result, we intend to diagnose and improve the model error related to the PBL scheme through the data assimilation. Okay, this is the last part of my talk. I will briefly introduce the challenge and my future work on data assimilation of MPD water vapor profiles. And there are 2 big assumptions for current data assimilation system. The first, we assumed a Gaussian error statistic for the model state. However, this assumption is valid for the observation for very stable variable and for large scale. But our water vapor variable observation, especially near the surface, it has very high variability in time and space. So this characteristic of water vapor violate this assumption. So for example, this light figure shows the distribution from the ensemble background of water vapor mixing ratio. The distribution of this background ensemble shows very skewed distribution, and it is very out of Gaussian distribution. So this skewed non-Gaussian distribution can result in suboptimal solution in current data assimilation system. And another assumption is that the observation error is assumed to be independent. This means that, for example, in our MPD profile data, the water vapor mix absolute humidity at one level is not correlated with other levels of observation, and even though they are from the same instrument. So for this assumption, usually current data assimilation system use diagonal component of observation error covariance. And to maintain this assumption, usually we try to remove correlated error of observation error. So we have conduct observing or thinning or averaging the data. For example, in the right figure, the upper panel shows the original our raw data of MPD, the time, height cross section, the raw data shows very detailed structure of MPD. It contains a lot of very important information. However, after thinning this observation for our data assimilation experiment, the low panel shows that by this thinning lost a lot of information. So we cannot make full use of this high resolution MPD profile. So this is the future work related with this issue. The first, I would like to assimilate MPD water vapor profile using a non-Gaussian data assimilation system, for example, the particle filter. And then I will develop and implement correlated observation error component in ensemble data assimilation system for high resolution ABL profile, such as the MPD and the flow lidar and ARRI data. And lastly, I will apply a more advanced vertical localization technique for our MPD data assimilation system. Okay, thank you for your attention, and I'm very happy to take all your question. Thank you.
Well, thank you, Junkyung, for your talk on improving weather forecasting skill by assimilating MPD water vapor profiles. I'm very glad that the technical hiccup experienced earlier didn't affect your presentation. We have time for questions or comments. May I remind the audience to please use the Slido interface located below the presentation screen to type your question. I'm sure there are fellow modelers in the audience who have some questions and comments. Junkyung, you presented a lot of motivation and a lot of information, certainly food for thought for the modeling community. So I liked your sensitivity study showing a sparser MPD network is better for a light precipitation, whereas for intense storms, you want a more dense network. So the science question would dictate the placement of the network. So if you were to set up your ideal campaign, like from a forecasting perspective, what types of convective conditions or precipitations would you like to have measurements for to help improve the forecasting skill? Or how dense or how sparse an MPD network would you need to help answer your ideal campaign science question?
Oh, yes, it's very important question. Yes, my sensitivity test result is just for, I think it can be not general. Okay. Can you hear me?
Yep, we can hear you very well.
Okay. Yeah, my result cannot. Is for. I cannot generalize our result for every event because this is just one case study. So maybe the other system and event have a very different result by assimilating the different configuration of MPD. However, I think this result implied that the targeted event, we have to decide the MPD and other observational network design according to our some targeted precipitation and other event. So because for example, we in the real data assimilation experiment, we target a very severe weather, like a very heavy precipitation, then maybe very heavy, very dense network of MPD and other profiling data would be very beneficial for this event. However, if we just interested in the other more light precipitation event and more, and for example, the more non-precipitation event, then we don't need to put a very dense observation MPD. Then it is enough to employ the more sparse density of that network. So this result implies that the meaning of this network design.
Mhm. Is there an MPD instrument that's running continuously in an operational mode that you use or that the model community can use?
I hope so. I hope so.
Is that the plan?
Yeah, yeah, because the MPD has very advantage over the current zoned data that is the currently used for the operational profiling data, because the MPD provide a more continuous and frequent update of the aural vapor field compared to the zoned data. So I expect the MPD have a more effect on over the zoned, the current profiling data set.
Thank you. We have a question from Hristo Chapilsky. Great work, Junkyung. Related to the Gaussian assumptions, have you run across situations in which the analysis of specific humidity becomes negative, such that you have to reset your analysis values before running a forecast? Looking forward to our work collaborating on non-Gaussian DA.
Thank you, Ristor. Yeah, it's very important question. In the Dart DA system, there are some function or option to prevent the negative value of specific humidity. So it prevent this negative value after data assimilation. However, I think it's very artificial technique. So maybe your non-Gaussian data assimilation system can handle this problem more naturally, and then maybe I can apply your method into my MPD data assimilation.
Great. Thank you, Hristo, for that question. We have a question from Ben Pickering. Thank you, Junkyung, very interesting. How transferable is the work that went into creating the OSSE for other researchers to use? Would it be difficult to run the same experiments and generate the same results on a different HPC system?
Yeah, thank you, Ben. Maybe from my experience, if I transfer our system, the model and data assimilation system into another HPC system, maybe it results in a very small differences because they have the different some computational system, but I think it can be ignored. So, but the most important thing is that which observation data set and the data assimilation system I will use. That is the most important and result in a very big difference result than the HP system. And also, we can also apply this similar OSSE approach to other observation data set. I know that you are very interested in the UAS observation data assimilation experiment. So, and it has a very similarity with our remote sensing profiling data. So I think our OSSE strategy can be applied for your interested observation set, UAS data set.
Great. Thank you, Ben, for that question. Looks like there's some collaboration happening, Junkyung.
Oh, I hope so.
Yeah, well, it doesn't look like we have any further questions. We are close to the seminar hour. If you are interested in Dr. Junkyung Kay's presentation or have further questions and comments or want to participate in a collaboration, please reach out to him via his email, which is provided in the seminar flyer. We actually, and Ben Pickering replied on the Slido, brilliant, thanks. Yes, that was going to be my follow-up question and you answered it. So on that last note, as a thank you from Ben, a thank you from us, on behalf of VOL, I would like to thank Dr. Kay on his excellent presentation, evaluating improvement in convective-scale weather prediction skill using MPD water vapor profile measurements. Thank you, everyone, and have a good day.
Thank you.